All right, here's the annotation of the free response question from the test from Thursday the 26th. It didn't go so well. First of all, it's calculator permitted, showing all the work, final units on every final answer, and 3 decimal places rounded or truncated, never using a rounded or truncated approximated answer for subsequent calculation. All right, so we're cooling our engine here. Suppose you're driving an automobile, a car or a truck or whatever have you, on a cold winter day, 20 degrees Fahrenheit outside, so definitely not here in New Braunfels. And your engine overheats, oh no, to around 220 degrees Fahrenheit. When you park your car, the engine begins to cool down naturally. You turn the car off, assuming. If the temperature T, which is in degrees Fahrenheit, we can assume, but it's nice to have it there for sure. If the temperature degrees Fahrenheit of your engine, T minutes after you park and turn off the car, satisfies this condition, or this equation, little t equals -9 natural log of big T minus 20 over 200, then answer the following questions. Okay, so first thing we want to make note of is that this is a function. There's only one variable on the right, so you could think of this as being a function that gives us the time, little t, as a function of the temperature. Whenever you're shifting from a variable expression to a numeric expression, you want to show that you're doing that, either by using function notation or just saying the words at a certain time. So very few people did that, little t of t, but there were a few that wrote it as using function notation. It kind of gets in the way when we're solving, so I'm going to go ahead and just use this version here. I'm going to go ahead and rewrite it down here. Little t equals -9 natural log of big T minus 20 over 200. All right, so my goal right now is to work in reverse to get at this t. So think about what you would do if you were evaluating this. You would plug in a value for big T. You would first subtract 20, then divide by 200, then take the natural log, and the last thing you would do is multiply by -9. If you haven't figured it out yet from Algebra 1, when you're solving for a variable, you're doing the inverse operations in the reverse order. So the last thing we did was multiply by -9, and evaluating it, the first thing you're going to do in solving is divide through by -9. Then you're going to unnatural log it. Then you're going to undivide by 200, and you're going to unsubtract 20. You're peeling back the layers in the reverse order using the inverse operation. All right, that makes sense. You've been doing that forever. There's no reason a -9 should get in the way. In fact, I'm not going to let it. I'm going to go ahead and divide through both sides by -9. Now, you don't have to show the division. This is a pre-AP level class, so you do not have to physically show that you're dividing both sides by -9. In fact, I would prefer that you did not. Just in your head, know that it's going to be t divided by -9, and it's gone from the left. All right, now, since the second to last thing we did in evaluating was take the natural log, it's the second step we're doing when we're evaluating. And you can either use the around the world, or I like to exponentiate. Since it's log base e, the base is implied e, I'm going to undo natural log base e, or log base e, by eing both sides. And we get e to the t divided by -9, which I'm just going to call that -t9. And on the right-hand side, e to the natural log of blob is just the blob, because they are inverse operations of each other. All right, so now I'm getting closer at peeling back the layers. Now, if the, I guess the third to last thing we did in evaluating was divide by 200, the third thing we're going to do is multiply both sides by 200. And again, you don't have to physically show that you're multiplying both sides by 200. I prefer that you didn't. Just go ahead and show a 200 in front on the left, and it divides out on the right, and we're left with t minus 20. We're rounding third, heading home. We're going to get it. We're going to score. The very first thing we did when we were evaluating it was subtract 20. So the very last thing we do when we're solving for t is add 20. And again, you can add it to both sides, and that isolates your big T. So I'm just going to put the big T on the left here, and I'm going to end up with 200 e to the -t9 power plus 20 on the ground floor. All right? That's important because the -t9 is in the exponent, but the plus 20 is on the ground floor. That now gives you the temperature as a function of time. So you could use function notation here if you want, because there's just a single variable. Again, although many people didn't do that, it's certainly worth looking for in the future. Okay, so either one of those is fine. So the way we graded this is, as long as you had a legitimate first move, you got the first check. Now, some people went from this line to this line they got rid of the -9 in a much more, I guess, equivalent, but not as nice manner. They condensed the log, and they brought it up and said it was to the -9th, and that would work. It does get rid of the -9 and clears the log, and then if you e both sides, you can exponentiate both sides by going around the world. So e to the t equals t minus 20 to the 200th to the -9. Now, here's why you didn't want to necessarily do it that way. You're trying to get at the t. You're trying to isolate the t. What did you just do? You kind of put yourself in a bind now because now the t is trapped. He's trapped inside that exponential. So, again, when in doubt as to what to do, imagine evaluating it going forward. How would you simplify the expression? Solve it by going in reverse. So, not incorrect, but not really the best route. So then you got one check for getting down to the final answer. Either one of these would work. All right, now part B, it says use your equation from part A. I remember that. We were just right here. To find the temperature, big T, the 3 decimals, after the engine has been resting for 5 minutes at T equals 5. Here's the advantage now of having this function notation, because all you'd have to do then is, in function notation, to show that you're plugging in a 5 for T, you would just get rid of those and plug in a 5 and a 5. Okay, super easy. If you chose not to use function notation, you do want to show that you're plugging in a 5 for T, and it's as easy as saying this: when T equals 5, colon, you're signifying your intentions. And then you get regular T equals 200 e to the -5/9 plus 200. All right, now those are both exact answers. But here's what you don't want to do, and we didn't take off if you did this. If you just have T equals, of course, 200 e to the -T9 plus 200, and on the very next line you say T equals 200 e to the -5/9 plus 200, it's kind of, it looks bad. It's kind of like you're lying mathematically, because by the transitive property, if T equals the top and T equals the bottom, you're saying that these two expressions are equivalent, and they're not. One of them is a variable expression, and one of them is a number, okay, and they're not always equal. They're only equal when T is 5. So get in the habit then, if you're not using function notation, to signal your intention by doing that little stage note off to the right, or use function notation when you have the chance, okay? Now that's an exact answer. At this point, all you have to do is go to the calculator and plug it in. So I have the calculator over here on the left, and we just type it in as we see it. 200, oops, I'm in y equals mode. Let me get my home screen. So from the home screen, 200e, which is second ln, and then raised to the -5 divided by 9th power. Click to the right, you're on the ground floor, plus 200. And you get your answer, and I have a wrong number in there. Hang on. I have too many 200s. Look what I did up here. And this is a good time to talk about careless mistakes and transcription errors. 314 is an unreasonable temperature, okay? So I'm catching my mistake here. 314, ooh, that's not good. I mean, we only started off at 220, and now I let it rest for 20 minutes, and the temperature increased when the outdoor temperature is 20. That means you did something wrong. And so notice what I did here. I was talking and maybe scratching my head and patting my belly and chewing gum at the same time. You don't know. But I copied it down wrong. I went from 20 to 200, and I added an extra 0 for some reason. That cost me, but thank goodness I'm thinking all the way through the problem, and now I can catch my mistake. So I'm going to take off that extra 0 at the end of both of those, and now I can come back and just recall my answer. Second enter recalls it. I'm going to come back here and reduce that constant by a factor of 10, and I get 134. That's a lot more reasonable because that's less than my initial temperature. Okay, so over here, T of 5, or when T equals 5, you get 134.750 if you truncate degrees Fahrenheit, or 134.751 degrees Fahrenheit. Okay, so we scored that as a 1 just for plugging in. So that'd be your third check if you plugged in a 5. And then we got another check for the correct answer. And if you have the units of degrees Fahrenheit, you're eligible for the overall unit point. Now, you can't just put degrees because degrees are not correct. Degrees could be like a unit of rotation, as we know now. It could be degrees Celsius. So you need degrees Fahrenheit. That is the specific unit. Here's a good word of advice. If you didn't know what the correct answer was, but you knew there was probably units tied to it, don't just put degrees Fahrenheit down as your answer, because it's not going to give you credit. But if you tie it to any number, like your favorite number in the whole wide world, mine is 127.74 because that's my birth date, written out in month, day, and year. As long as the units are tied to a numeric answer, you could still earn the unit point. Of course, you're not going to get the rest of the point, but it's worth getting all you can. I would just suggest knowing how to do the problem and getting all the points, okay? All right, so part C then. As your car cools, you call your talkative best friend to come pick you up. After what seems like an eternity, you hang up the phone and find that your car's engine temperature is now at 65 degrees Fahrenheit. So that's your current temperature. That's a big T value. How many minutes have passed since the time you parked your car, which remember that's T equals 0, to the time you hung up the phone? So now we're trying to find T. So we have two equations now. We have this equation that I gave you that has minutes solved already as a function of the temperature, and we have this one here that we just found that gives us the temperature as a function of time. Many people use their equation from part B to answer part C, and there's nothing wrong with that, but you're just redoing all the algebra. The reason that we have two different equations is depend on what we're given and what we're trying to find. So when you're given the temperature, it's easier to use this one. So I'm going to go ahead and write it again right here. I guess I can just copy it. I have it right here. Let me just lasso it with scissors, one of my favorite things to say and do. And again, if you keep it in terms of function notation, then it's real easy. You could just say, okay, when the current temperature is 65, that's little t of 65. And that indicates that you're plugging in a number. It's -9 natural log of 65 minus 20 over 200. If you didn't do that, then the alternative would be to say when big T equals 65, colon, and then you're just going to plug all this in here and just set it equal to T, little t in general. T equals that. All right, so it's not imperative that you use function notation, but what is important and required in the future is that when you're shifting from a variable expression to a numeric expression, you have to indicate that you're doing that. All right, so you got another point here for plugging in for T, 65. So I forgot how many checks that is now. We're on the 5th check. And then simply evaluating it, and since it's an expression, we just plug it in again on the home screen, -9 natural log of, and I'll go ahead and use the alpha y equals numerator of denominators. It's a stressful environment. I'm not going to trust my math and do 65 minus 20 in my head, especially when I have my calculator here. So I'm going to use it when I can. And I'll just double check now. This is the beauty of math print. You can match it up and it looks good. And you get 13.424. 13.424. And notice how I'm working straight down. I have equal sign. So I really have T of 65 equals, and again, that's time. So the units are going to be minutes, which I'll abbreviate MIN. Or if you round, you have 13.425 minutes. So some people are getting like 13.7 something. I don't know where you're getting rounding error, but don't have rounding error. All right, now is that a reasonable amount of time? Yes, it's reasonable. We started at 0, and we know up here that after 20 minutes it was down to 135. Hang on, let me come back up here. After 5 minutes it was 134. So now we're down to 65, so it had to be more than 5 minutes. And 13 minutes is certainly more than 5. Some people added 5 back to this, and you don't need to do that. The model already takes into account the running clock from T equals 0. So you were on the phone with your friend for some amount of time that was already included in this as your car was cooling. So then you got the 6th check for the numeric answer, one of the two, and you're eligible for the unit check if you have it there. All right, and then part D, according to the given mathematical model and equation, if you were to leave your car parked in the same place for several days before getting back to it, what would the car's engine temperature be? And then I add another hint here, that is, what is the limit as T goes to infinity? Well, by referring back to the mathematical model, we're basically assuming that the outdoor temperature stays 20 degrees Fahrenheit. So that's my way of showing that if the outdoor temperature stays 20 degrees Fahrenheit consistently, and you let your car sit for a long, long time, it's reasonable to think that your car's temperature should be approaching the temperature of the outside ambient air temperature, which is 20 degrees. So on this one here, all you got to do is put 20 degrees Fahrenheit. right? The car is going to be approaching the temperature that it is outside. According to the model, it's 20 degrees. You got one check then for the answer. That's the 7th check. And one check now if you have your units on everything. That's one way to do it. Okay, that's the easiest way to do it. For those of you who are mathematically inclined, the limit as t goes to infinity, well, let me come back up here and get this equation. As time goes to infinity, so that's my independent variable. So I want to find the version where time is my independent variable. That's my equation that I solved in part A. So let me take that, and I'll lasso that. And I'm going to bring that down below, and you'll see what we can do this a different way mathematically. Okay, so if I get rid of that, and now in front of there, I take the limit as t goes to infinity of that expression. You could do one of two ways. You can go to your calculator, and you can't plug in infinity for time, but if you just let 2 days go by, okay, that's t equaling 72 hours. Look what happens when you just plug in a 72. You get 200e, which is, again, second ln, to the negative 72 divided by 9 plus 20. I mean, that's what the question was really asking. You get 20.06, okay? But I said the limit as t goes to infinity, so let's let a little bit more time pass. If you just change the 72 hours, which is really 3 days, right? Instead of 48 for 2 days, I'm sorry. Let's just change it to 99, and look what happens. It gets 20.0033. So you can see that as you're letting the time increase, getting bigger and bigger, your temperatures appear to be decreasing, approaching what is 20. Now you can kind of break your calculator. If you type in a number that is, let's say, just add another 9. If I add another 9, I'll have to make sure I divide by the 9 again. Your calculator can't handle the decimal overflow, and it just defaults to 20. Now, according to the model, it's never going to reach 20, and that's probably a good thing to consider because your car is insulated. So there are things that are going to keep it from reaching outdoor temperature. But for all practical purposes, it approaches 20, and it does reach 20. So that's another way to do it. You can also think about what the graph of this looks like. Your parent function is e to the t power, which has a horizontal asymptote, and it's monotonic increasing. There's y equals e to the tth power. The 200 in front increases it, or vertically stretches it by a factor of 2. So it looks like that. There's 200 e to the t. What would the negative do? That's probably the most important one. That's going to reflect it across the y-axis. So now it's going to look something like this. And now it's a decreasing function. The 1/9 is going to be a horizontal stretch by a factor of 1/9, or by a factor of 9, sorry. And that's just going to change its shape, but it doesn't change its location. The plus 20 is important because that moves everything up 20 units, and that's going to change the horizontal asymptote. So our final shape is this guy right here, which I'm highlighting in red, but now it's going to be moved up 20 units. So there's your horizontal asymptote. And if you just draw it monotonically decreasing now, what happens to that graph as you go out to the right on the x-axis as you let t approach infinity? Well, the graph is tapering off, approaching the horizontal asymptote, which once again is at 20. And because 20 is a temperature, degrees Fahrenheit was needed on this last part to get the unit check. Now, a lot of people answered that as infinity. And again, if you're just thinking about what's reasonable, is it reasonable to suspect that if you let your car sit outside in 20-degree temperature forever and ever and ever, that eventually the car is going to get infinitely hot? Whoa! Man, maybe if you parked it on the sun, but not if you park it in 20-degree temperature. So again, people who did that were losing sight of the fact that it was an exponential function that you can evaluate by plugging in, that you can look at the graph. They forgot what the outdoor temperature was. And so most people who put infinity did not also put degrees Fahrenheit, which means they lost the unit check right there because they just put infinity, no unit check. But by leaving it off also, they didn't realize that it didn't make sense that a car can be approaching infinite degrees Fahrenheit. That's like 1,000,000 degrees Fahrenheit. That's even bigger than that. Makes no sense. Okay? And hopefully if you would have realized you were finding a time, or a temperature, sorry, a big T, and you put degrees Fahrenheit, you'd realize that infinity didn't make sense. and then you can think about the question differently. So the idea of these questions are to get you thinking all the way through. All right? Get thinking all the way through. And so that was worth 8 checks, and there you go. So on your free response on Wednesday, it's going to be another log problem. It's going to be another calculator problem. We're probably going to be a little bit pickier with the notation. So again, remember, if you're going from a function that has a variable in it to evaluating it at a point, it's best, especially if there's more than one variable, to just say when t equals 5 and then plug in. If you only have one variable on the right, feel free to use function notation t of 5. It's a little bit cleaner, but either one works, all right? And units on every single answer, which can help catch a careless mistake of a gazillion, jillion degrees Fahrenheit. That is a hot rod if I ever heard of one. All right, good luck. Practice, practice, and practice some more and repeat.